Okay, our next talk is on prospects for new eV-scale sterile neutrino searches. It'll be presented by Josh Spitz from the University of Michigan and Daniel Winklehner from MIT. I'll let you go ahead.
All right, can you see that and hear me?
Yes. Mm-hmm.
Okay. Well, thanks, Kyle, for that great talk. I completely agree that beta decay is very cool, and that's really the theme of this talk as well. Daniel Winklehner and I will be talking about new eV-scale sterile neutrino searches, and the organizers have asked us to present Juno Tau, Prospect 2, and Isodar. So here's a brief outline of our talk. First, I want to give you a feel for the eV-scale sterile neutrino landscape. And then I'd like to motivate electron flavor disappearance searches using beta decay within that landscape. And then we'll go through each of these three experiments we've been asked to discuss. Okay, so I'd actually like to start off this talk with a conclusion slide, which has been taken directly from my talk at this conference 8 years ago. The talk was feature short baseline sterile neutrino searches with accelerators. So here's the slide. The conclusions I drew from this talk 8 years ago were that the discovery of a light sterile neutrino would be a monumental result for particle physics and cosmology. The light sterile neutrino issue needs to be resolved. But unfortunately, a truly definitive resolution is difficult to achieve and will likely require multiple detectors and experiments. And one point of emphasis I also made is that these kinds of experiments, while they're completely highly important and impactful for trying to solve the sterile neutrino issue, also produce a lot of other important physics and R&D as well. And unfortunately, 8 years later, the experimental situation is more complicated than ever, as we've been hearing in this conference. And a brief summary of the situation remains largely the same. We have anomalies, we have null results. The world is pursuing this physics in earnest, but again, truly definitive experiments are very difficult to achieve. We have learned some things in the past 8 years or decade, if you will, and we should be proud of what we've learned. So I've made a sort of a brief list of, I think, the main points about what we've learned in the past decade. We've learned that with 95% confidence, less than half of the mini-boon low energy excess is due to electron neutrinos from microboon. We've also learned that the muon flavor disappearance along baseline and atmospheric experiments continue to see no indication of a signal at high delta M squared, except for baby ice cube, which sees 90% perhaps hint of muon flavor disappearance. In consideration of global data, 3+1 sterile oscillations are effectively ruled out, but there are some viable alternatives to explain one or more of the anomalies. We've continued to learn that reactor flux modeling is quite hard. A great example of this comes from the 5 MeV bump, which is seen across many different reactor experiments and has nothing to do with oscillations involving a sterile neutrino. The reactor sector is, of course, an evolving situation with new data coming out frequently. But the latest and greatest is that there is no evidence of the rate-only reactor anomaly with the recent Kirkatov Institute uranium-235 to plutonium-239 beta spectral ratio. And in addition, no single reactor experiment sees spectral oscillations at more than 3 sigma. There's also less room for steriles coming from tritium beta decay measurements, Catrin, as well as cosmological observables like large-scale structure and CMB anisotropy measurements. But we have seen a positive signal, a modern confirmation of the gallium anomaly coming from the best experiment at the 4 to 5 sigma significance level. Okay, so these anomalies still continue to represent one of the most important indications of new physics we have. But again, the situation is complicated and confusing. It's quite hard to make sense of the global data. Is this new physics or not? Are one or more experiments have one or more experiments made a mistake. And I think that answering this question requires multiple experiments, including with muon and electron flavor and with appearance and disappearance. So we clearly have a continued motivation to search for oscillations involving a sterile neutrino. I'd also like to, in particular, motivate electron flavor disappearance searches. So you can see this nice table coming from the white paper on light sterile neutrino searches. We have our 4 categories of anomaly given by the 4 rightmost columns, and then various different physics models that attempt to explain each anomaly. Of course, remembering that possibly a systematic or non-novel physics might explain one or more of the anomalies. But you can see that if more than one of the anomalies are due to some kind of consistent underlying new physics, it's likely that sterile oscillations are involved. So you can see the check marks over here, green check marks, orange check marks, and these 5 rows, the first 5 rows, involve oscillations with a sterile neutrino. So if you want consistent underlying new physics to explain one or more of the anomalies, oscillations involving a sterile neutrino is probably your best bet. In addition, I'd like to draw another conclusion from this table, which is that reactor and source experiments, which represent the rightmost 2 columns, are uniquely sensitive to the sterile hypothesis without many complications from other new physics possibilities, which tend to be at higher energy scales. Okay, what's the latest and greatest in electron flavor global sterile results? We saw some similar results previously, but just to show you again, this nice plot is from this paper down here, by the way, and it contains sort of the 5 different electron flavor disappearance sectors that people search for. So this is within a 3+1 model. We've got delta m squared versus sine squared 2 theta. All the lines are drawn with 2 sigma confidence. We have the reactor spectral global line in black, the gallium allowed region in purple, the Karman and LS&D NUI on carbon-12 cross-section measurements in green, the Catron result in blue, which assumes that the lightest neutrino mass is 0, and then the solar result in pink. And you can see at this threshold of 2 sigma, the only closed contour is actually gallium currently, but it's around 5 sigma and not in conflict with reactors for some of the parameter space, as you can see. So you can combine these results in various ways, and these authors do that. And these plots are from this recent paper. So you can consider a reactor and solar combination on the left here. You see some allowed regions and some limits as well. And then you can also combine the reactor and gallium results, and again see some allowed regions. So the overall conclusions in terms of the latest and greatest in electron flavor disappearance searches are shown here. We have the electron flavor anomaly, which is now driven by the gallium result, especially in consideration of the new best result, which we just heard about from Steve. We've got large portions of parameter space, which are found to be in mutual agreement between gallium and reactors. The reactor anomaly rate only measurement, the rate only reactor anomaly is gone, and each individual reactor spectral analysis is less than 3 sigma significant, with the strongest hint coming from neutrino 4, and then solar neutrino experiments are in tension at the 3 sigma level. All right, so I hope I've motivated continued searches for oscillations involving a sterile neutrino, and within that landscape, electron flavor disappearance searches. So with that in mind, Daniel and I will present 3 future electron flavor disappearance searches at short baseline, the Juno Tau and Prospect 2 reactor-based experiments, and then the ISODAR accelerator-induced source experiment as well. So the overarching concept behind these experiments is that you start with an intense source of electron antineutrinos, beta decay. You have your reactor source where your fission fragments beta decay with over 1,000 isotopes contributing to the new bar spectrum. Or you can have a source, maybe usually a single isotope, which beta decays to provide this new EVAR. And you take that source and you couple it to a nearby detector, and you look for inverse beta decay interactions occurring on your free protons inside of your detector. And you can try to look for L over E dependent oscillation wave, which would be indicative of oscillations at short distance scales, which is an indication of a mixing with a sterile neutrino. In terms of these experiments, there are a number of important considerations. You're looking for oscillations occurring at very short distances, so you'd like to have pristine knowledge of what you start with. So you'd like to have excellent knowledge of your flux. You're trying to measure a L over E type of oscillation, so you'd like to have high precision energy and baseline resolution. These are neutrino experiments, so you have to worry about stats, and then you'd also like to mitigate backgrounds as well. Okay, so let me tell you about Juno Tau, which is a reactor-based experiment. This is, of course, within the context of the overarching Juno experiment. You can get a feel for the Juno FAR detector on the top right here. Juno is, of course, the most ambitious reactor experiment ever, which will feature 20 kilotons of liquid scintillator with 78% photo coverage at 53 kilometers from a 27 gigawatt thermal power reactor complex. You can get a feel for Juno rate versus electron antineutrino energy on the right here. This is the oscillated spectrum expected in 6 years of data taking. And this really extraordinary experiment will provide amazing sensitivity within the 3 neutrino oscillation paradigm. It expects to have the world's best measurements of both delta M squared as well as theta 1,2, and even has sensitivity to the orientation of the neutrino mass hierarchy, as you can see in this plot over here, which shows the difference between a normal ordering and an inverted ordering. So primarily to obtain a reference spectrum for the Juno FAR detector 3 neutrino oscillation measurements, Juno will utilize a near detector, which is called Juno Tau, at 30 meters, which will feature ultra high energy resolution to measure these oscillations. And excitingly, this detector, Juno Tau, will be taking data quite soon. So a little bit more about this near detector for Juno. Juno Tau will be 2.8 tons, 1 ton fiducial volume of gadolinium-loaded liquid scintillator at 30 meters away from a 4.6 gigawatt thermal power core at the Taishan nuclear power plant. You can get sort of a feel for its location proximal to the single reactor core over here. It will go in this room 10 meters down inside of a basement. There's another core nearby, but only about 2% of the IBD rate that Juno Tau will see will come from this core up here. So yeah, primarily we'll provide this reference spectrum for Juno, but Juno Tau will also be sensitive to the nuclear reactor spectrum fine structure. That means that this detector will be sensitive to individual isotopes in their IBD rate measurement. And given the strong energy resolution and high stats and low background, Juno Tau will also, of course, feature strong sensitivity to oscillations involving a sterile neutrino. Just to give you a feel for the detector, you can see it will utilize these tiles of silicon photomultipliers, 94% coverage of SIPM tiles in this detector. So this excellent photo coverage with 10 square meters of SIPMs combined with this high liquid scintillator light yield and also amazing photon detection efficiency means that Juno Tau will have sub 2% energy resolution at all energies. You can compare that energy resolution versus reconstructed energy. Here's diab. You can compare it to diab as a reference spectrum, the Juno FAR detector in red, and then Juno Tau is even better than the FAR detector. So given this, the ultra high energy resolution, the high IBD event rate of 2,000 events per day, the low background given this basement location, Juno Tau will indeed provide world-leading reactor-based sterile oscillation sensitivity. And you can see that in this plot over here within a 3+1 model of delta M squared versus sine squared 2 theta. You can see the gallium anomaly in this allowed region in red, prospect 1, a Reno-Neos combination at 5 sigma, a recent global fit from 2019-2020. And then in blue, you can see how well Juno Tau will do with 3 years of running at 5 sigma. All right. Thank you. Daniel Winklehner will take over and tell you about Prospect 2 and Isodar.
Hello. So let's move now to a slightly different area of that plot that that Josh just showed. So you can see, yeah, there we go. And he showed the exclusion, the sensitivity plot for Juno Tau. And I want to point out that there's a large area in the high delta M square region that is not covered by this, and this is exactly what Prospect 2 is planning on looking at. So Prospect 2 was already discussed in the first sterile neutrino session, so I'm going to try, in the interest of time, to go over this a little faster. Has the aim of probing electron antineutrino disappearance from high delta M square sterile neutrinos, which will be a test of the gallium anomaly and the reactor antineutrino anomaly. And there was already a Prospect 1 run that provided important results, but it suffered from some technical issues. There was some loss of active volume due to liquid scintillator entering the PMT housings and causing electronics failures. And also they noticed some light yield degradation over time, which was likely due to liquid scintillator contamination from materials that were touching the liquid scintillator volume. Here are some images of the original Prospect design, which was run at the high flux isotope reactor HIFER at the Oak Ridge National Laboratory. And here you can see the reactor core. It's very small, so this is another important factor for the success of Prospect and Prospect 2 is that there's good knowledge about the origin of the neutrinos. And here you can see the detector. It's a 4-ton lithium-doped liquid scintillator detector that consists of segments. It's 14 by 11 segments, 118 centimeters long. And the detection of the electron antineutrinos will be through inverse beta decay with a 1.8 MeV threshold. So with the pulse shape discrimination, this provides an excellent antineutrino signature and greatly suppresses backgrounds. And there were some nice results already. It demonstrated observation of reactor antineutrinos in an above ground detector setting with good energy resolution and well-controlled backgrounds. It set some limits on eV-scale sterile neutrinos, as pointed out in this plot here. The black line is the sensitivity, or the limit in this case. And all of these were taken from this paper on the archive. And also, it did some Prospect was able to do some precision measurements of the reactor antineutrino spectrum from uranium-235. This is shown here on the right side of Prospect at HIFER. Now, the Prospect 2 detector design is mostly an upgrade from Prospect, addressing these challenges that I mentioned earlier. Many things are unchanged. The segmented design is unchanged. The lithium doping is unchanged. It's still, of course, inverse beta decay detection and background rejection for detector segmentation and pulse shape discrimination. But the principal design change is to move the PMTs outside of the liquid scintillator volume and then do a slightly higher lithium loading, increase the length of the segments, and this will increase the IBD rate to roughly 1,150 events per day. Prospect 2 is envisioned to have a signal to background ratio of 4.3, and this will give them a nice result, hopefully over the course of 2-year deployment at HIFER, where again it will probe the RAA and the gallium anomaly and do some more precise measurements of uranium-235 antineutrino spectrum and the absolute flux measurement of antineutrinos from uranium. So here is the same plot that you saw earlier, but now with the green dashed line showing the sensitivity that's expected from prospect 2, and you can see now that this where Juno tau covers a large area of the lower delta M squared and of course the gallium anomaly, the prospect 2 will cover the higher delta M squared region. So this is a great reach, covers much of RA and gallium anomaly up to 10 eV-squared, and there are a number of posters that I urge you to look at this conference. Before I move on to the next experiment, let me show you the wish list that I came up for neutrino experiments, and that to really provide a definitive experiment to answer the sterile neutrino question, and that is to have a high flux, which will be high statistics, continuous operation, again high statistics, a well understood neutrino spectrum. For example, this could be from a single isotope decay, and then you would like to do shape analysis to distinguish different models, like a 3+1, 3+2, or a 3+1 in decay, or if these wave packet effects are indeed present. In addition, you might want to have some significant overburden for background reduction, and of course good detector resolution both in position and energy, and this will then give you a definitive experiment. Now the ISODAR at YEMILab experiment claims to be just such an experiment. Here you can see a CAD model of the ISODAR at YEMILab experiment, where the source of the neutrinos is brought to the detector instead of the detector being brought to the source. ISODAR consists of a compact cyclotron, as shown here on the right, that produces a 10 milliampere proton beam at 60 MeV, and this translates into a 600 kilowatt beam we use about 1 mole of electron antineutrinos from pure lithium-8 decay at rest. Then 17 meters center-to-center distance from this neutrino production target is the liquid scintillator counter. ISODAR expects to see about 2 million inverse beta decay events over the course of 5 years, and also about 7,000 electron antineutrino electron elastic scatter events. This experiment has been pre-approved to run at the YEMILab facility. The caverns are already constructed. On the left, you can see a photograph that was taken during the excavation of the LSC cavern. On the right, you see the already completely excavated cyclotron cavern. These, of course, look a little different now. They have been completely finished and also covered with shotcrete. There are 2 papers that you can look at, one physics paper about ISODAR at YEMILab, and then the conceptual design report about the underground installation. YEMILab is an underground facility, and you've already heard quite a bit about YEMILab in the introductory session, in the opening session. It's an underground facility at Mount Yem in Korea. It's operated by the Institute of Basic Science, IBS. It sports about 1 kilometer of overburden for shielding from cosmic ray muons. The excavation, as I said, is already finished, and the proposal for the LSC detector is underway. And one nice thing about this mine is that there's actually drive-in access, and that makes the installation of the cyclotron and the target feasible. Now, the detector itself is a 2.26 kiloton liquid scintillator detector. The inner volume is 15 meters in diameter and 15 meters high, and surrounding that inner target volume is a buffer zone of 1.14 kilotons and then an outer video of 2.4 kilotons. The outside is covered in photomultiplier tubes, and this is giving ISODAR at YEMILab, or this is giving the LSC an energy resolution of 6.4% per squared energy and a vertex resolution of 12 centimeters per squared energy. The total inverse beta decay detection efficiency should be around 92%. Now, in order to provide the high statistics that this experiment needs, a completely new accelerator has been designed. And the reason why this was necessary is that the requirements are quite high. It needs to be a robust, compact machine that's also hopefully cost-effective and produce a continuous wave beam at 80% duty factor, and this is just for maintenance, of 10 milliamperes of protons at 60 MeV. This is a 600 kilowatt beam, and this is not something that a commercial cyclotron has been demonstrated to do so far. But for the ISODAR project, a new type of cyclotron was developed that can address all these challenges. What are the challenges? They are all related to space charge, which is the Coulomb repulsion of like-charged particles in a bunch, which leads to beam spread, nonlinear behavior, controlled and uncontrolled beam losses, and all of this together leads to activation of the machine. And there is actually a limit that was determined at PSI, where the beam power deposition in the extraction region of a cyclotron should not exceed 200 watts. Now, all of these have been addressed in the ISODAR project. It's a room temperature compact cyclotron that operates 4 double gap cavities, which leads to very high energy gain per turn. And then there are 3 novelties that are in this design, and one is to accelerate H2 plus ions instead of protons. Another one is to inject axially through an RFQ to efficiently pre-bunch the beam and cram as many particles as possible into the tight phase window that this cyclic particle accelerator can accelerate, and to utilize an interesting beam dynamics effect that was also discovered at PSI, but never actively used in the design of the machine, and that is called vortex motion, where the bunch actually turns locally and curls up into a tight ball in a motion not unlike a hurricane or a vortex. The target, of course, needs to be carefully designed as well. It needs to withstand 600 kilowatts. The target itself consists of a set of nested beryllium shells that are cooled by heavy water. This is shown here in the very center. And then this target is bombarded with the protons, acts as a spallation neutron source. The neutrons then capture on the surrounding lithium-7 that you can see in gray here on this picture. The lithium-7 becomes lithium-8 and almost immediately beta decays, yielding your electron antineutrinos. The spectrum of this is very well understood, can be very well predicted. It peaks around 6 MeV and has an endpoint of about 13 to 14 MeV. And here on the right, you can see a CAD model of this target. Now here you can see the nested beryllium shells that I already talked about, and a computational fluid dynamics and finite elements analysis study was undertaken to show that this target can really withstand this type of beam power. Okay, so all of this together makes ISODAR a very unique experiment, providing high statistics, high resolution with a low background, with a well-known energy spectrum of the neutrinos, and a very compact electron antineutrino source, which then leads to a very robust LWE shape analysis. And this I can show here. On the top, you can see the primary physics goal of ISODAR, which is a search for sterile neutrinos. The interesting thing about ISODAR is it can actually distinguish between models with 1 sterile neutrinos, 2 sterile neutrinos, or sterile neutrinos that decay. It would also be able to see a wave packet effect and so on. It also has an unprecedentedly high sample of elastic scatters at low Q, and that would give a very nice measurement of the weak mixing angle at low Q, and also let's isolate the non-standard interaction analysis. There are even more physics that are not directly maybe neutrino related. One is a search for axion-like particles or ALPS, and the other one is a bump hunt in the neutrino spectrum that could lead to the finding of light X particles that are producing the target that can decay to neutrino-antineutrino pairs, or it might elucidate a little bit more the platinum bump if it's oscillation related, which I understand it's very unlikely. So in conclusion, there are many short baseline experiments with neutrino sources from accelerators, reactors, or radioactive sources, and many of them hint at beyond standard model physics. Some of these anomalies could be explained by sterile neutrinos, as Josh explained. And as he also said, we need a really definitive experiment. And the three experiments that we chose in this presentation would give us on timescales from 2 to 5 years coverage of the most important regions in the parameter space of the delta m squared sine squared 2 theta of, in this case, a 3+1 model. So over 2 years, prospect 2 would cover the high delta m squared. In 3 years, neutrino tau would cover the low delta m squared. And then on a scale of 5 years, isodaric GEMILAB could give you a full coverage, as you can see here on the black dashed line, of high and low delta m squared, covering nicely the reactor, the RAA and the gallium anomaly. And with this, I would like to thank you very much, and Josh and I will take questions.
Right, thank you very much. That was a really nice talk. We have a question from Emilio Clufoli. This one is to Josh because it's related to the Juno Tau detector. And the question is, in Juno Tau, can the fine structure of the reactor neutrino spectrum create some problems for the sterile neutrino search?
Sure. So, the fine spectrum from the fine structure from individual isotopes is expected to present as sort of this step-like structure coming from the endpoints of Newey bar spectra. And their sharp drop off. So I guess it depends on delta m squared somewhat, but the sinusoidal L over E style signature of oscillations involving a sterile neutrino, I think, is very unlikely to be confused with that sort of step structure from the individual isotopes.
Okay. All right. Well, then, with that, I think that's all of the questions for this talk, and so we can continue discussions related to this on the Slack channel, as with all of the discussions throughout this session.